Okay, in section 15.3, we're going to be getting into buffers. Now here's a titration curve, and we're going to handle this as if it were a weak acid. And we're just going to take a look at different points along this curve. We want to be able to just kind of say, how is a buffer produced in a titration? What does that buffer do? And what species are present along the different points all along this curve? So identify the major species present. That's just kind of a way to say the ions or molecules present at each of the following points on the graph, and compare their concentrations to one another. So let's go back to that graph and look at all of these different points. If this is a weak acid titration, we're assuming here we've got a weak acid, we're adding sodium hydroxide, and we're getting a conjugate ion and water. All right, let's rewrite our equation here at the top. We've got HA and OH minus to make water, and our conjugate base. And we start out, this equation doesn't even apply until we add some of our sodium hydroxide. So we start out here at point 1 having only the HA. If no sodium hydroxide has been added yet, then this equation doesn't even apply. So this is just a weak acid problem at the very beginning with no base added. And then what we're looking at here along the curve is a limiting reactant problem. We get to a point where everywhere in here between points 2, 3, and 4, all the way up to 5, the sodium hydroxide is going to be limiting. And then I'm going to go out of order here a little bit so we can see. And then we get to the equivalence point where we have no acid and no sodium hydroxide, and we only have our conjugate, A minus. So at the equivalence point, we have the weak base only. So everywhere in there in the middle, between those points, is the hydroxide is limiting. That means I have HA, I don't have any hydroxide, and I have my A minus. Okay. So in this region here, between 1 and 2, we have a lot of HA, and we're slowly building up the concentration of A minus. So right now, because we're making the A minus, in that region my HA is bigger than the A minus. Right here at point 2, that's my midpoint, and that's the point where the hydroxide is still limiting, but it's neutralized half of my acid, and the concentration is equal to the A minus. And then from points 3 to 4, the concentration of A minus keeps getting bigger and bigger and bigger until that's all that's left. So here it's really the story of the HA slowly getting neutralized, the concentration going down, going down, going down, going down until it's gone, right at that point 5. So from point 2 to point 5 here, where 3 and 4 are, we have our A minus is increasing in concentration, and it's actually greater now than the HA. And we get to the point where there's only A minus left. And then after that point, we got to go back up to our equation. After that point, we now have excess hydroxide. Okay, excess hydroxide. So if we go back over here, I'm going to scribble these out because it won't let me erase them. When we have excess hydroxide, now all my HA is gone, we have excess hydroxide, and we still have our A minus there. So this just really becomes a strong base problem. How much strong base do we have left over? Okay, recognizing some of the buffers just by looking at their formulas. Are these mixturous buffers if we have equal volumes of 1 molar solutions of these are mixed? So we want to get rid of spectators when we see them to see if we just want a weak conjugate pair. Here we've got HNO3, which is a strong acid. That's immediately going to rule that out for being a buffer because strong acids cannot make buffers. Here we have HNO2, which is a weak acid, and sodium nitrite. If we get rid of the sodium, because that's going to be our spectator, we have a conjugate pair there. That is a buffer. NH3 conjugate NH4+, which is right here, ammonium chloride. Chloride is the conjugate of HCl, that is neutral, so we're going to get rid of that as well. And we have NH3 and NH4+, that is a buffer also. Next, we want to see if we can make a buffer by mixing solutions together. So this one gets a little bit trickier because you have to think about balanced equations. But let's see what we have. KOH, equal volumes, equal volumes of the substances that are mixed together. We have KOH mixed with CH3 and H3Cl. So here's that positive amine, that NH3 group on the hydrocarbon. Whatever this is called, it has a chloride on it. We want to recognize that chloride as a spectator. And then the equation here is really hydroxide plus CH3NH3 plus makes water, and CH3NH2. Now in this case, if the KOH and the CH3NH3 plus are both 0.1 molar and equal volumes, means they're going to the molarities we can look at to see how many they have moles. That means this is an equivalence point problem where this is gone, this is gone, because they have equal amounts and we only have the conjugate. So that's really just a weak base problem in A. So that's not going to work. In B, we have KOH, strong base, CH3NH2. Well, that NH2 is an amine, that's a weak base. When I have two bases, they won't even react. So that is not going to be a buffer either. Okay, so we just want to see what's going to happen, what type of solution do we have. In A, we just had a weak base problem. B, we have a strong base and a weak base, so this is just going to be a strong base problem. When we look at C, we have the same reaction, the hydroxide plus CH3NH3 plus. We do not want the chloride spectator, makes CH3NH2 and water. Okay. Now this one in C we have 0.2 molar sodium hydroxide or potassium hydroxide and 0.1 molar CH3NH3 plus. That means that I have, this is my limiting reactant now. I have excess hydroxide, and I'm going to generate that when I make this. So that again, now once this reaction is over, I have a strong base and a weak base. The strong base will give me the pH, but that's not a buffer either. So if we look at D, one more, same equation, OH minus CH3NH3 plus makes CH3NH2, methylamine plus water. So if we look at, now we have 0.1 of the potassium hydroxide, 0.2 of the CH3NH3 plus. That's going to tell us that our hydroxide is limiting. Now I have the CH3NH3 plus, and we've generated the methylamine. That is a conjugate pair there. This is a buffer problem. We generated a buffer in question D. So not only do we need to look at the balanced equations of everything, we also need to look at the molarities and volumes to see, once they react, can we make a buffer as a resulting solution. We get to a problem then where we need to do some math. Calculate the pH of a 0.5 liter solution that contains formic acid and sodium formate. And then, separate problem, calculate the pH after we add sodium hydroxide. So let's just do the first part here. Here we have a conjugate pair, sodium formate and formic acid. So this is a buffer problem. We do not need this volume because there are no volume changes yet. That volume was going to be useful down here in part 2 when we have 10 milliliters of the base added. So if this is a buffer problem, we just need Henderson-Hasselbalch. Probably the fastest way to do this. pKa for this is going to be 3.74. Okay, which, remember, that would be the pH if my conjugate pair were equal, my buffer pair were equal, plus the log of the base over the acid. So since I have more base than acid, 0.2 over 0.15 molar. If I have more base than acid, then I would expect my pH to be just a little above 3.74, a little more basic than that. That's a way to do it without a calculator. We just want to estimate. We can see it's a little higher. 3.87 is going to be our pH. Okay, now this gets a little harder when we add the sodium hydroxide because we're going to have volume changes, so we need to get everything into moles here. So let's restart and calculate everything from scratch here. First thing we need to do, we need a neutralization reaction. So we're going to have the sodium formate, and we're adding a base, so it reacts with the acid, the sodium formate, and it's going to make the formic acid, or I'm sorry, wow, I've said all of that wrong. We have the formic acid, and it's going to react with the sodium hydroxide, because that's an acid and that's a base, and it's going to make the conjugate, the formate ion, HCOO minus plus water. And we need everything in moles, and since acids and bases react with one another, and there are volume changes, this is just a limiting reactant problem. Everything's going to be in moles. So now we need that 0.5 liters. So 0.5 liters times 0.15 molar formic acid is going to give me 0.075 moles of formic acid. 10 milliliters of 12 molar sodium hydroxide is 0.12 moles. And then half a liter of 0.2 molar sodium formate is going to be 0.1 moles of that. And as we never care about the liquid water because it's the solvent. In this case, we can see that the formic acid is limiting. It's 1-to-1 ratios. So let's get rid of 0.075 from those guys. And then we're going to add it to my conjugate, my products. And we're going to get 0.045 moles of the hydroxide, 0.175 moles of the formate ion. We need to get those back in molarities, 510 milliliters now, because we added 10 milliliters of the base, and my sodium hydroxide comes out to be my hydroxide rather, 0.0882. The sodium portion of that is a spectator. 0.0882 molar. And the HCOO minus becomes 0.343 molar. This is a strong base, and my formate ion is a weak base. So the pH of this solution is going to come from the strong base. So negative log of my strong base, 0.0882, is my pOH, which is 1.05. My pH then is going to be 12.95. Okay. So here we can see that as soon as I have excess hydroxide, as soon as this buffer capacity is reached, which means all of one of my substances has been neutralized, the pH changes dramatically, 12.95, because the pH was around 3.74 is where the buffer region exists. So 12.95 is a big jump above that. The last problem then just looks at the Kas and Kbs exclusively and says, how do we choose a conjugate pair to make a buffer? So if we wish to buffer a solution at a pH of 10.07, which of the following bases and conjugate acids would be the most useful, assuming we have their conjugates with them, which this problem does. We want, as we've said in the past, it's the midpoint. We want the pKa to be about the pH. That means we have equal concentrations of the conjugate pair, and that's a really good buffer capacity. So we want our pKa to be around 10. First thing we're going to highlight here is pHs and pKas. Those are dealing with acid quantities. We do want a basic pH because it's 10.07, so it's good to look at these three bases. but these are all Kb values. So if at first glance we're tempted to say pH of 10.07, this Kb of 10 to the negative 10th looks really promising, but that's a Kb, and we need a Ka, pKa around 10. So what we need to do is we need to solve for all of these Kas, and if you know how that works, they're all related times to the water. 1 times 10 to the negative 14th equals Ka times Kb. Then you could probably just estimate their exponents the other way and figure out ahead of time that it's going to be this ammonia is going to be the best choice, because 10 to the negative 5th will give you a Ka that's about 10 to the negative 9th, 10 to the negative 10th. So let's calculate those anyway. The Kas of this one, the ammonia, is 5.5 times 10 to the negative 10th. The Ka of C6H5NH2 is going to be 2.38 times 10 to the negative 5th. And then the last one is 1.04 times 10 to the negative 8th. So here we've got our Ka, our pKa, 5.5 times 10 to the negative 10th would be the closest one to that. It doesn't have to be perfect. We just need it in that range.